And we come to the next speaker of this session before the coffee break, which is by Richard Wylde from Thomas Keating, who is actually one of the project partners. And he will talk about quasi-optic ideas and components. I think this will be a little bit general and about how to build EPR systems. So, Richard. Okay.
Firstly, Ryan, can you hear me? Is this working?
Yes, we hear you.
And that's appeared on your screen. I think rather like Joris, you seem to get the preview as well, because I think if I move to the full screen mode, I lose it on this screen. So thank you, Rainer and your colleagues, for organising this. And as you're right, this will just be a rather general talk on one aspect, in a sense, of one part of this project, the EPR part, and in particular, the sort of quasi-optics part. And I'll come right at the end to describe what you're looking at now, which has a tenuous but definite link with EPR, but it's not what you might think. So this really is a talk about, in a sense, and it's a pretty simple one, the physics and engineering of getting information containing signals to and from an EPR sample buried deep in high field and high homogeneous magnets. So there's a question, why do you want to use quasi-optics? And I'm including corrugated guides. I'll describe what those are in a minute, rather than conventional waveguides, which you might see at lower frequencies, X-band systems, and so on. Firstly, the corrugated guide is extremely low loss. The losses you may see in these systems, or a corrugated guide of perhaps a meter or more, will be at the 1 dB level or much lower. And that's obviously important when power is so expensive to make at these frequencies, the so-called sort of terahertz gap. The second thing is that the optics you use to process this can be made frequency independent. And that allows one to build multi-frequency spectrometers with the ability to look at samples at different frequencies without extracting them, and the cost in time and so on, and loss of the identical form when a sample is removed. We have a view that we like using reflecting optics in our systems compared with using lenses, because the standing waves, which are a plague in millimeter terahertz systems at these frequencies when losses are low, are much lower when you haven't got the ability for standing waves to build up in lenses and between lenses. But Alexander touched on this. One of the real powers over traditional waveguide systems coming from lower frequencies, and generally in this whole quasi-optical instrumentation area, is the ability to use polarization to code information, which is not possible in many other sort of transmission systems at these frequencies. So I should say this is not really a highly technical talk. This is just one part of the Peter project. I thought of it, but I want to leave you with some of the ideas behind this, so that if any of you want to pick up and work in this area, I've given the odd pointer to where you might go. This is a slide actually taken, really quite old now, from drawn by my colleague Graham Smith in St Andrews when he was building a 94 gigahertz high-powered system. basically illustrating the problem in many of these EPR spectrometers. You're putting in fair amounts of power, and you want to listen in very short timescales to very much lower power. And the problem is that you need to get very, very low levels of reflections within the system so that your original injected power doesn't dominate over the very small levels of power that are coming back from the actual EPR interaction. So, and if you want to do that and have these things of very low loss and low contamination, then we and I think the world had taken the view that this process of doing quasi-optics is the way to do it. But what is quasi-optics? It's basically it's the free space propagation of electromagnetic waves, but waves when the beam size is only a few wavelengths across. So the beams suffer from diffractive spreading of the beam. This is not geometric optics where you can draw, straight lines on a sort of a diagram of the optics. The beams expand as they propagate away from their minimum size. So the basic theory of looking at how these beams expand and therefore how you can control their expansion actually goes back to the 1960s in the context of people wondering how developing analytical tools about how lasers work. And Kogelnik and Lai, there's a reference there to a paper, is the basic analytical tool, and it's really very simple. So you look, when you have a beam, to something called a beam waist, which is the point in which the beam has the smallest lateral extent and has a flat face front. So if you could have a device that moved across that beam waist, it would have a constant phase. So unlike a geometrical optics where you would have a focus, the beam waist is a sort of quasi-focus, but is definitely not a single point. It has extent. And basically a beam can be characterized by its width. I hope can you see my pointer? Characterized by the symbol W, and a curvature on the beam. For a monochromatic beam, a single frequency beam with single polarization, if you know what the size is and the curvature is at one point, then you can determine exactly what the size and curvature will be at any other point, just by looking at these two parameters, the beam waist size and the radius of curvature. And there are some really I make my living, Thomas Keating makes living out of these very, very simple formulae, which can be used to calculate how a beam will propagate in what can be potentially really quite complicated circuits. And the sort of view that we take, and this is sort of drawing on the process of moving up from, in the EPR world, up from lower frequencies, X-bands where it was traditionally done into higher frequencies, is that we take the view that there are analogs of, in quasi-optics, are basically all the microwave components. So I've sort of enumerated them here. Waveguides are just free space. If you want to change the phase of something, you have moving mirrors. You can split beams up with polarizing grids or which set polarization, or independent of polarization, though with some frequency development with films. You can have absorbers, you can have attenuators, and more importantly, and this is particularly true of systems where loss is low, you can have devices that act as isolators or circulators, sort of lobster pots, things which seem to go in one direction but not another. And it's very simple. You can plot out, here's a little CAD program we have that shows how beams propagate through, in this case, just a simple circuit for material measurements, where it's conventional just to plot the side of the beam at the 1/E amplitude level. But core to this, as in all of these quasi-optical systems, is the need to produce beams that have a Gaussian form. We misuse the English language by calling the current design of antennas that we produce sort of Ultragaussian, which of course in a sense is a misuse of language. But the theoretical plots you can see on the left of this screen show how Gaussian down to, and I'm afraid this is sort of an engineer's rather than a scientist term, down to -40 dB, 1 part in 10,000 or so. And these are theoretical models, but you can see here that one can actually match a theoretical model and the measured result to actually quite extraordinary precision. This is a plot actually operating, and again, to illustrate that this process can work at high frequency. This is a plot at 600 gigahertz. So often, twice the sort of frequencies that many of the EPR systems we're working at are. And the black line is the theoretical prediction, and the red and the green line, both in amplitude and phase, is the pattern. So this illustrates that the analysis of corrugated feed horns, the feed horns that inject these Gaussian beams in, is well under control, and there's a sort of pretty picture here in two dimensions. But of course, I mentioned a couple of minutes ago, a core instruction or device that is really needed in these systems because they're so lost and suffer from standing waves are isolators, devices that will send signal in one way but not in another. And those in quasi-optics are formed by the use of freestanding polarizing wire grids, illustrated here and here, and of which you can see a picture here, and these are repeated in many of the quasi-optical systems. But then on top of that, the really curious property, and this is obviously out of the magnetic resonance world, so people here in this community will better understand it, that you can use the gyromagnetic properties of ferrites off of strontium or barium ferrites, which are tolerably transmitting in the microwave a millimeter wave frequencies. They have some loss, which is a nuisance, where you can couple to the spins in such system to develop devices which are non-reciprocal, and so that one couples to one of the circular polarizations as it propagates through the piece of ferrite. The beam couples to that, but in the orthogonal polarization clockwise instead of counterclockwise, there is no coupling. And the really strange thing about the world is that works in the same sense when you reverse the beam. This leads to really quite complicated behavior and resonances. And here is a picture of, again, a decade old or so, of measuring a transmission through a piece of ferrite, where in the high frequencies, you see the normal dielectric resonance that you get with a slab of any dielectric, but really quite complicated and remarkably well matched to our theory structure are the parts that are to do with the magnetic resonance. And these allow one to produce isolators or circulators with really quite significant performance. So at W band, 100 gigahertz, one can easily get 40 dB of isolation. And again, if we return to a slide for 10 minutes ago, the ability to cut down standing waves and isolate power is extremely important in EPR systems, so that one doesn't see, one isn't swamped by the original source power. At low, near to the resonance in these structures, then the devices of relatively narrow band move away for that up to the frequencies that Peter in other projects, such for Alexander are then, is that these things actually turned out to be really quite wide band in the level of isolation that you can achieve in them, although the losses in this case a little over a dB or so are rising. So that's a crucial component in EPR systems. Also crucial are the need to make absorbers so that signals can be terminated. And this is a slide of some work showing that cone absorbers that we often use in these systems can have really quite remarkable early low reflectivities. This is a measurement coming from a set of cones used in astronomy, but can show that one can have reflectivities down at 60 dB or so. You've seen and will see more pictures of the system for Peter, but here is a picture of work that we did in my university in St Andrews by my colleague Graham Smith, which incorporates all of these devices, as well as, and again Alexander touched on this, the use of what's conventionally called inductive mode, the ability to distinguish between an EPR absorption and a non-polarization, non-EPR-based absorption. And this is a very powerful technique of injecting one polarization and looking at orthogonal polarization, and only the EPR interaction produces this orthogonal polarization. Here is a picture of that. I should say that Quasi optics can be applied in a whole set of other detection mechanisms. This is some work that we've been doing in Johns Hopkins University, again in the frequency range of hair, where an EPR generating interaction is applied, but the detection is through changing the polarization of neutrons coming from a neutron producing reactor. And so microwave detection, millimeter wave detection, as in the Peter project, is not the only way in which Quasi optics can be used to apply microwave millimeter wave signals. So if that's broadly what this short talk on Quasi optics covers. If people are interested in taking it further, there are a couple of front cover of books here for people to pick up and study if that's of interest. And finally, the Thomas Keating's really in the business of building instruments, and just to leave people with an odd thought that there is sort of unity in science. And we build instruments. EPR is a significant part of our activities, but it's not the only part. And so I thought I'd just leave my short talk with this picture here, which is a measurement done again half a decade ago by a cosmic background measuring experiment, measuring the magnetic field across the cosmos, the central part of this being our Milky Way. It's a measurement at the similar frequencies that occurs in EPR. And what's really quite interesting is that we built the antennas to pick up and generate that signal. Here's a picture of them. There's a flood of them here. And the theory behind how these corrugated antennas work in cosmology came out of work done primarily by my colleague Graham Smith in St Andrews and others for EPR. So here is an example of the sort of cross-fertilization in science that techniques developed for EPR are now involved in measuring the in this case the cosmic background and determining the age and how much dark matter and dark energy there are in the universe. So I think you've probably listened enough to me. If I can hand back to Rainier, and then the symposium can continue. Rainier.
Okay, thank you, Richard, for this very nice overview on quasi optics. Are there any questions? So yeah, Alexander?
You have to unmute.
You have to unmute.
I'm still muted. Thank you for this nice introduction, what you are doing there. I was very interested in this neutron scattering thing which you showed. This is an optic not for neutrons, but for microwaves which excite samples to polarize them for neutron scattering experiments, right?
It's on a reactor just north of Washington, Gaithersburg. And basically, yes, so I think we are polarizing the system, and then the effect will be in the neutron scattering.
It's a dynamic neutron polarization in analogy to EMP.
Yeah, so that's, I mean, I must admit, I haven't heard from them. I must talk to them. One, I should emphasize, one of the puzzles of being at the sort of instrumentation generation business is that it can often, for experiments, and Peter will be one of them, that it can, we do our work, and then it can take a number of years for people to, if you like, debug and get their instrumentation up to the peak of performance that they need for it. But this was one, you're perfectly right, that EPR, I'm trying to control my mind, but basically it had a transmitter system of 2 detectors, so that they were tuning, they were doing full EPR in order to make sure that they had tuned the system to do the polarization of the neutron systems that were then picked up by the neutron scattering.
Mm-hmm.
So it needed to be a full EPR system. It wasn't one Mark was just sort of throwing millimeter wave power at the system and wanted to check that it was actually that the field matched the frequency, so that they knew the system was tuned.